All right, so now we're going to discuss this concept known as variational error analysis. And if you will, it comes from the observation we saw before that the time h flow of the Hamiltonian vector field is equal to the discrete Lagrangian map, discrete Hamiltonian map associated with the exact discrete Lagrangian. Okay, so put another way, if you could compute the exact discrete Lagrangian and used it to generate a symplectic map, then it's going to agree with the time h flow of Hamilton's equations. So this naturally leads to the following question, right? So is it possible then, instead of analyzing the order of accuracy of a numerical method in terms of these maps, is it then possible to evaluate the order of accuracy in terms of, it's like this exact discrete Lagrangian? Can you do the error analysis in terms of the discrete Lagrangians themselves, and how might one go about doing this? Right, so the question is the following, right? If you have a computable discrete Lagrangian, let's say LD, that approximates LD exact in the sense of a map from Q cross Q cross the rails, if you will, where rails have to do the time step to the rails, right? Can we say something about the order of accuracy of the associated discrete Lagrangian Hamiltonian maps? Okay, so of F tilde LD. Okay, so that's the question. All right. So in order to do that, it's like we need to talk about the extent to which a discrete Lagrangian approximates the exact discrete Lagrangian to a certain order of accuracy. Okay, so we say that LD is of order R, okay, if there exists an open set subset, let's call that U sub V, contained in the tangent bundle with compact closure and constants CV greater than 0 and HV greater than 0, such that, okay, the difference between LD Q0 QH H, okay, minus well, this is just a scalar value function, so I just need the absolute value of the difference, right? Q LDE Q0 QH, and there's this again implicit dependence on H, right? So we want a H there because when we talk about order of accuracy, it's like we always talk about some sort of error which grows like some power of H, right? So we want to have that H there to see how that behaves. And so this is less than equal to this constant times H to the R plus 1. So the truncation error is big O of H to the R plus 1, right, for all solutions Q of T of the all Lagrange equations with initial condition Q and Q dot, which is in this open set, and H, which is sufficiently small. Okay. All right. So again, we say that the discrete Lagrangian is of this order if an estimate like this holds. Okay. And the basic idea, if you will, is the following: that if you have control over this kind of error, it has sort of global control over the error, then what's going to happen is that you have some control over the sort of the discrete Legendre transforms, okay, which are generated by the discrete Lagrangian and the exact discrete Lagrangian. And since the map, the discrete Lagrangian and discrete Hamiltonian maps are obtained by taking compositions of the discrete Legendre transforms and their inverses, right, then by some sort of inverse function theorem type argument, you can conclude that, you know, this condition implies something about the order of, you know, now the discrete Legendre transforms, and then together the implicit function theorem that implies something about the approximation power of the discrete Lagrangian or Hamiltonian maps. So that's more or less where the argument is going. All right. So, okay, so we talked about the order of the discrete Lagrangian, and then the next thing is to talk about the order of the discrete Legendre transforms. Okay, so this is sort of discrete Legendre transform. Order. Okay. And then now there has to be a norm, because now that's actually takes values in a sort of, it takes values in momentum basically, right? So basically F plus minus LD, right, of discrete Lagrangian LD is of order R if, again, there exists an open set let's call it UF now, okay, which is contained in the cotangent bundle, okay, with compact closure again, and constants. Let's see, CF, which is greater than 0, and HF, which is greater than 0, such that, you know, sort of the obvious estimates hold, right? So now you have some sort of norm of F plus LD Q0, well, Q at time 0, Q at time H, H minus F plus LD exact now of Q at time 0, Q at time H, again with that fixed time step, and this norm less than equal to CF H to the R plus 1, and then something similar happens here. Sorry, this is a blackboard bold F plus LD Q0 and QH, sorry, minus, right? And as before, it's like this is for QT, which are solutions of the all Lagrange. And initial conditions. which are in the appropriate set. Okay. So it should be TQ again, and Q dot, well, I should say, and initial conditions. Q dot in this UF, and H less than equal to HF. Okay. All right, so now you have this notion of order the discrete Legendre transform. All right, and then now we are in a position to state a theorem. Okay, and the theorem basically is that given a regular Lagrangian, right, L and a corresponding Hamiltonian H, the following are equivalent. Right, for a discrete Lagrangian. LD, okay, which is the first one is that the discrete Hamiltonian map of LD is of order R. Okay, the second one is that the discrete Legendre transforms of LD are of order R. And the third one is that LD is equivalent to a discrete Lagrangian of order R. Okay. All right. So I'm not going to prove this, but I will at least sort of make the following comment about the last equivalent statement. And the reason why I say that LD is equivalent to discrete Lagrangian of order R is more or less that if you take a discrete Lagrangian and you add a constant to it, then clearly it doesn't change anything in terms of the symplectic maps it generates or the numerical method it generates, but it would then not agree with the exact discrete Lagrangian, as you might expect, to any order. Okay, so what you need to do is to somehow, it's like look at discrete Lagrangians which are equivalent in terms of the symplectic maps which they generate, and there's a way of characterizing that equivalence. But as I said, a simple example of this is if you shift it by a constant. And more generally, it's like if they differ by essentially something like a total time derivative, then, yeah, so in any case, so if LD is equivalent then to a discrete Lagrangian of order R, then essentially one direction of the argument is fairly straightforward. Going from here to here to here, it's relatively straightforward. It more or less has to do with the fact that if LD approximates the exact discrete Lagrangian to this order of accuracy, then because the discrete Legendre transforms are defined in terms of derivatives of the discrete Lagrangian, right, that sort of approximation statement implies something about the approximation of discrete Legendre transforms and having the same order. And then finally, it's like the equivalence to the first statement has to do with the fact that if you have then a discrete Hamiltonian map, the discrete Hamiltonian map is given by the composition of a discrete Legendre transform and its inverse. So if you remember, right? The discrete Hamiltonian map is from Q0, P0 to Q1, P1, right? This is what I called F tilde LD, right? And this is the point Q0, Q1, which projects to the left by F minus LD and to the right by F plus LD. Okay, so this F tilde LD, which is the discrete Hamiltonian map, is given by just the composition of F plus LD with the inverse of F minus LD, right? So again, more or less, it's like what you show basically is that if the discrete Legendre transform, it's like has order R, it's like then by some sort of implicit function argument, the inverse of that has order R as well, and then the compositions, it's like have order R, right? So going from here to here to here, it's like more or less, it's like it's based on that kind of argument, and in some sense, that's perhaps the more important direction, right? So one needs a little bit more care to show that are all equivalent, but at least the sort of the most relevant direction, which is that if you could construct a discrete Lagrangian which approximates the exact discrete Lagrangian to a certain order of accuracy, then it's like it induces a numerical method with that order of accuracy. Okay, and so this is more or less, it's like the framework of what's called variational error analysis. What it does then is that it reduces the problem of constructing, say, high-order variational integrators to the problem of constructing high-order discrete Lagrangians. Okay, and there are systematic ways for doing this, which we'll discuss later. All right, so I'll stop here for now.